Hello, welcome to my presentation on our work, verifying low-dimensional input neural networks via input quantization. I am Kai from MIT CCL. This work is co-authored with my advisor, Martin. Let me first introduce our motivating example, the ACAS Xu benchmark. This benchmark has been widely used in the neural network verification research in recent years. The goal of the system is to provide flight control advisories to avoid potential collision. The system takes 7 inputs as shown in this table. These inputs are mostly speed, direction, or distance measurements of the ownership and the intruder. Note that the input space is discrete, with application-specific grid points. The system provides 5 output scores for these 5 possible actions. A higher score means a lower probability of collision if we take this corresponding action. Traditionally, we can use the Markov decision process to model the process and use dynamic programming to compute the optimized responses given the sensory inputs. These responses are stored in a large lookup table. The problem is that the lookup table is too large to be efficiently embedded in flight control systems. So a promising solution is to use neural networks to approximate or compress this lookup table. The neural networks also provide score interpolation for inputs not on this lookup table. Since the behavior of the networks is hard to predict, researchers have developed verifiers to check if the networks behave as expected. These verifiers face multiple challenges. First, verification is often slow. It can take minutes to hours for some hard cases, and it does not scale well with respect to the neural network size, because the verification is fundamentally exponentially expensive regarding the network size. The verifiers are also unsound with respect to floating point arithmetic, because they cannot afford the complexity to accurately model the floating point computation details in the neural network inference implementations. And they have been shown to produce wrong results in certain cases. If we want to support new neural network architectures, we may also need to invest significant manual effort to develop new verification algorithms. So in this work, we propose to add an input quantization layer to these networks, so that we do not use the network as a score interpolator, but map all the inputs onto the grid points. This input quantization also enables efficient verification by enumeration. So here is more detail. The input quantization preserves the grid points in the lookup table, which means that the original points in the lookup table are the same after quantization, but the other points are mapped to the nearest point in this lookup table. And during training, we can actually reuse the pre-trained network and prepend the quantization layer to the network, so there is no need to retrain the networks. At runtime, this input quantization is equivalent to the nearest label interpolation. And we quantize each dimension independently so that it can be efficiently implemented in the target flight control system. And this nearest label interpolation has been proven to provide sufficient accuracy for the ACAS tasks. To verify these networks, we can simply enumerate all the points in the quantized space and check if the corresponding output meet the specification. The complexity of this verification is then bounded by the size of the quantization space. So we conduct some experiments to test our method. We train small and large networks using the data generated by the open source horizontal ACAS system. And we verify the property phi9 in the ACAS Xu benchmark. The real var is a traditional neural network verifier. It can be seen that its verification scales poorly for this large network. By comparison, input quantization is quite efficient and it scales well on these large networks. And the bottom row of this table shows the time to verify the network on all the quantized points, which is the upper bound of verification time for any safety properties. So we show that these problems faced by the traditional neural network verifiers have all been solved by input quantization. The verification is fast now because the complexity is bounded by the lookup table size, and the method scales linearly with respect to the neural network size. The verification is also complete and sound. We can enumerate the output of the networks on the target implementation to generate the exact floating point computation results. And it also becomes trivial to support new neural network architectures, and in fact we can support new or any floating point programs in general. So to summarize, we have shown that input quantization enables efficient, complete, and sound verification. This method requires that the quantization provides sufficient accuracy for the target application, and the quantization space should be sufficiently small to allow efficient enumeration. On the other hand, neural network verification research has made tremendous progress in the recent years, and it is time to move on from these simple benchmarks such as the ACAS Xu.